All right, so this is part 2 in our stoichiometry of precipitation reaction. So this is the second example. I'm going to basically do an overview of part A, the mass of the precipitate that forms, and spend most of the time focusing on finding that concentration molarity of the ions. I'm also going to set it up just a little bit differently from the first video, just to give you another format that you can go ahead to do your calculations with as well. So again, the first thing you're going to have to be able to do is to write those precipitation reactions, the double replacement reactions, making sure you're identifying the correct precipitate. Looking for, like in this case, you have group 1 and nitrate ion. So these two ions are always soluble. This has to be your aqueous ion, which means that your iron 3 hydroxide is going to be your precipitate. And I've also balanced it. And then down here, I've just written the information from up above in terms of the amount and the concentrations of each of these that are going to be placed into the mixture for the reaction to occur. So for part A, this is similar to the beginning of the year. The only thing you really need to look out for is that you're starting with your volume of your each of your reactants, and then we're going to use its molarity to get into moles. So first thing to do is just get the reactant to molarity, and then I'm going to go ahead and use my mole to mole relationship, the stoichiometry part of my equation, and then I'm going to go ahead and just go right to grams so that I know how many grams each would be able to produce. So once you actually get these two amounts, so I've done it for iron 3 nitrate and our potassium hydroxide, I can see that the potassium hydroxide produces the lowest amount of grams. So that's going to be the amount of precipitate that forms. That also tells me then that the KOH is going to be my limiting reactant, and my iron nitrate is going to be the one that's going to be in excess. Okay, which I need to know for my next calculation. Okay, so that's the first part, just figuring out precipitation, which is just using the volume and molarity in order to complete the stoichiometry. Now, with the second part, now we're going to get into how to figure out the concentrations of our ions in solution. So what I want you to think about is we have iron ions, we have nitrate ions. Okay, these are the ones that were in excess. I also have potassium ions to think about and my hydroxide ions to think about. And this was from a part of my limiting reactant. So if I first look at my limiting and I look at my potassium hydroxide, the hydroxide is going to be the one that completely gets consumed to form the iron 3 hydroxide. So there will be no hydroxide ions left over into solution. These were completely consumed. However, K plus ions are spectator ions. Okay, so those are going to be fully present. If I now look at my reagent excess and the ions that are present in that iron 3 nitrate, I know my nitrate ions are going to be completely present because those are also spectator ions. And it's going to be my iron 3 plus ion. I'm just going to circle a dotted line. This is the one that I'm going to have to figure out the partial amount that's left over in the solution. So this has a partial amount left over in the solution that I'm going to have to find the concentration of. Okay, so just like in the last video, I'm going to just figure out the concentration of my 2 spectator ions, and then I'll deal with my iron 3 plus ion. So again, I'm going to write this out a little bit differently just to give you another format that you could use. So I'm going to first focus on my potassium ion. So I'm going to figure out how much I had present based on the reactant. So that was a 0.0550 liter solution that had a 0.180 molarity, so 0.18 moles per 1 liter. Okay, that again is just coming up to looking at my potassium ion and how much I had present in the potassium hydroxide solution. I can then go ahead and say that for every 1 mole of potassium hydroxide that was present, I had 1 mole of my K plus ions. So that gave me 0.00990 mole of K plus ions. I can now go ahead and find the concentration of it by taking that mole that was present, because all of that stayed present the entire time in solution. Okay, however, it's now in a larger volume, so I have to change my volume for that. So that's going to be 0.0350 liters plus my 0.0550 liters. Okay, when you do add those up, you do get 0.0900 liters, which I'll end up using later on. When you divide those two, we get our concentration of our potassium ion that is still and left over in solution after the reaction, which is 0.110 molar. Okay, I'm now going to go ahead and do that for the other spectator ion, my nitrate. So I'm going to start with the iron nitrate solution, this one up here. So I had my 0.035 liters of a 0.25 molar solution. So I'm going to again start with my volume, 0.0350 liters, using the concentration again of the iron 3 nitrate, which was 0.25 mole per liter. Be careful here on this next step. For every 1 mole of FeNO33, okay, I had 3 mole of my nitrate ions. Okay, when you go ahead and plug all of that in, you're going to get 0.0263 mole of nitrate ions. Okay, so this is how many ions were present in this solution originally. So now I just need to find the new concentration in the new ion, since again, they were spectator ions and they're present the whole time before and after the reaction. So for my nitrate ions, I can now take that number of moles that was formed. Okay, I'm going to use my combined volume, which was at 0.0900 liters. And when I find that, I get my 0.292 molar solution. Okay, so those are 2 of my 3 concentrations. So I have figured out my concentration of my potassium ions, my nitrate ions. So now it's just a matter of figuring out how much of my iron 3+ ions are still in solution after some of them form the precipitate. So now I'm going to focus on here my Fe3+ ions. So I usually say the first thing I want to do is find the initial amount that was present. So I'm going to use, in that case, I'm going to start with my FeNO3 solution. So I'm going to take that 0.0350 liters of it that had a 0.2 molar concentration, or sorry, 0.25 molar concentration. For every 1 mole of my iron 3 nitrate, I had 1 mole of my iron 3+ ions, which means initially in my initial solution before the reaction, I had 0.00875 moles of Fe3+. Okay, so that was how much was there to start, but we know that's not all present at the end. So now I can go ahead and find the amount that was consumed. Okay, so how much was actually taken out of solution and formed the precipitate. And here I'm going to start with my limiting. Okay, so with my limiting, which is my potassium hydroxide, I had 0.0550 liters of my KOH. I'm going to get that into moles. I'm then going to say that for every 3 moles of KOH that reacted, I had it react with 1 mole of my FeNO33. Okay, that's just using their coefficients from the original balanced equation. And then for every 1 mole of FeNO3, I had my 1 mole of my iron 3+ ions. So when I get that, I get 0.00330 moles that was consumed. Okay, so now I'm just going to look for the difference between these, and then I can go ahead and calculate my concentration. So how much then was left over? Okay, I would have my 0.00875 mole minus, so that's how it was initially in the solution before it reacted, minus this 0.00330 moles of what was consumed to make the precipitate. So I get 0.00545 mole. Okay, I can now find my final concentration of my iron 3+ ions using that mole amount that I just calculated, divided by that same total volume, the 0.0900 liters, which is going to give me 0.0606 molar concentration. Okay, and that gives me my last one. So I have my concentration of my iron 3+ ion that's left over, and then I have my concentrations of my 2 spectator ions. Okay, so there is a lot of work involved with finding these concentrations, but again, you got to find the best kind of bookkeeping method to keep track of your mole amounts and your new volume concentrations so that you can be effective at getting each of these.